welcome back to circuit analysis one course. Okay, we are in topic 10 now. Okay, so today topics on Norton's theorem. But before I go on to Norton theorem, I want to give you one more example for Thevenin. Okay, so for this example, we want to find a Thevenin equivalent circuit. Okay, for terminal AB right here. Okay, so in the previous examples, it's always open at terminal AB, but this time there's RL load resistance of 60 ohms connected to it. Okay, to apply the Thevenin theorem, okay, the definition saying that your VTH is the open circuit, right, at the terminal that you want to find. So what we have to do is we have to remove RL first such that it will be an open circuit. So remove RL such that this now become your V open circuit, which is equal to V Thevenin. Okay, so then you analyze as you would have. Okay, so you look at this picture, right? So your VTH is nothing but, right, your VOC, nothing but if the current passing the voltage across R1, because, well, if you have 40 milliamps coming out here, right, come to this junction right here, come to the junction right here, it's supposed to split right into here and into here, into R2 and R1, but R2, this is open already, so therefore there's no voltage drop across the R2, so all the current go through here, and also that means VOC is simply a voltage drop across R1, and the voltage drop across R1 is 40 milliamps passing through R1, so 40 milliamps times 90 ohms equal to 3.6 volt. Okay, now what about RTH? Well, RTH, you have to open your 40 milliamps, right, turn it off, so 90 ohms, and this is 30 ohms, and this is terminal AB. So you look into here, right? So your R total is equal to simply 30 in series with 90, which is 120 ohms. That's it. So therefore your RTH is 120 ohms. So your Thevenin equivalent circuit consists of VTH of 3.6, right? 3.6, and your RTH is in series with your 3.6 volt of 120 ohms. So this is AB. So when you want to give a final answer or analysis, okay, you reinsert back your load that you took it off right here. You insert it back. This is 60 ohm. So you get, this is your equivalent circuit. If the question asks what's VAB, right? VAB from the previous problem, this is VAB. Okay, so VAB is a voltage drop across the 60 ohms. Okay, so therefore, in this case, when you has put into the Thevenin, it's become very easy, right? So you can use voltage divider. So VAB equal to RX 60 over R total, right? Well, R total in this case is the 3.6 volt divided into the 120 in series with 60. Okay, and this is of course VAB, is divided out of the 3.6 volt, so you get 1.2 volt. So this is how we can apply the Thevenin, to solve certain problems. Okay, so now I want to go into Norton's theorem. Okay, Norton's theorem is, it's not a theorem to make your circuit easier. Okay, whereas Thevenin, it represents your complicated circuit with a voltage source and series connected resistors. Okay, Thevenin resistance. But for the Norton theorem, you, instead of a current source, instead of voltage source, you have current source. And you have Norton resistance, which is a resistor parallel to the current source that you've drawn. Okay, the definition of Norton current, IN, is that it's a short circuit current between 2 points in the circuit. And RN, the Norton equivalent circuit, Norton equivalent resistance, is the same way as you found your Thevenin equivalent resistance. It's the same values. Okay, it's just the position is different. Okay, RN is parallel to current source. Okay. right? So therefore, examples right away. This is the example. Okay, this example right here. I want to find the Norton's equivalent circuit at terminal AB. Terminal AB, right here. Okay. So therefore, IN is a short circuit, right? So first I remove RL. I remove RL out. So when I remove RL, it becomes this picture. This circuit right here, AB. Okay. And it says that IN is a short circuit current at the terminal that we want to find. So therefore, we short this, and this is your I short circuit or equal to IN, your Norton current. Okay, you can use whatever you want. You can use dividers, you can use mesh. Okay, but for me, I like dividers. So I go, well, where does this IN come from? Well, it has to come from the source. So this become I total, right? Then it's split into this here and this here, right? IN. So IN split out from I total. Okay, so I find I total first. So to find I total, right, it would be 83.3 volt because the current I total passing through 83.3 divided by R total, right, because this voltage source 83.3 take care of this R, and this R. And how are they connected? This one 100, right, 47 are connected in parallel. So 100 parallel with 47, right? And then it's in series with the 47 ohm right here. 47 ohm right here. So therefore, I total turn out to be 1.05 amps. Okay. Then when I have my I total, right? I have my I total. Oops, sorry. I have my I total. I total here. When it's split into two paths, right? IN. This is 100 and it's 47. So therefore, IN is equal to, if you would go back and sort of look at the way I do my shortcut current dividers formulas, okay, when you split your current into two channels, okay, two branches, okay, so I can write right away IN would be equal to 47 divided by 100 plus 47 times I total, right, which is equal to 1.05. So equal to 47 over 147 times 1.05 amp. So therefore the answer is 336 milliamps. Okay, then so you get your IN. To find RN, right? It's the same way as to find RTH, Thevenin resistance. Okay, so therefore I short my voltage source, so I short my 83.3 volt, right? Look in here, what's R total? So seeing this, you will see that 47 and this 47 is in parallel. So 47 parallel with 47, right? And then you add with 100 ohms plus 100 ohms. Okay, so therefore it's equal to 124 ohms. Okay, so this is your RN. So therefore, this is your Norton equivalent circuit. Okay, and then you reinsert your RL back in and you get this answer. Okay, this is Norton equivalent circuit. Okay. Okay. In this case, to find RN. Okay, to find RN. Okay. So let's see. This is the case that they want to show that we can find it using that general formula, right? When we insert the test source inside. Okay. So therefore, let's see. Oh, no, sorry. My mistake. Okay, my mistake. Let's do it. Norton equivalent circuit. So in this case, see, what do we do? This is 3 volt. Okay, we want to find the Norton equivalent circuit at terminal AB. Okay, so first I remove this out, remove this R out. Okay, so you get open circuit, right? So it becomes this when you remove that R. So So you get terminal AB to be open. So it become like this, AB. So then I short it, right, to find IN, right? Short it, okay, to find IN. So therefore, in this case, let's see, what can I do to find IN? So I redraw it. Now I pull this 3 volt out to be like this, right, this position, because when I do that, I can see that there's a 3 volt across here, right? There's a 3 volt. Hold on. See, this sometimes you have to sort of like rearrange your circuit. So there's 3 volt across here, right, from this terminal and this terminal, because they are parallel, right? And they're actually parallel to this 2K and 1K. See, if I draw it like this, 2K, 1K, right, like this, 2 milliamps minus plus, right, 3 volt, and this is actually my IN, correct? Because my IN flow like this, come out here, right, passing through the 3 volt like this, okay? So this is my IN. My IN, right? So that means, well, they're all parallel. Can you see that? They're parallel here. So there must be a 3 volt across this 2K and 1K. 3 volt like this also. Okay, I want to find IN, right? This is the node. This is the node, right? So therefore, I have 2 milliamps going in, right? Minus IN already, right? IN's leaving this node right here, right? KCL. Let's call, this is node C or something, okay, at C. See? And then this current, there's a current, this current on this branch right here, current, right? But then the positive and negative is in this direction. So according to Ohm's law, my current should enter the positive like this. So let's call this I1. So my I1 is a current passing through the 2K and 3K in series, so 3K ohm. So that means my I1 is equal to, my I1 would be equal to, can I get, oops, sorry. Where did it go? What happened? Here, right here. My I1 would be equal to 3 volt over 2K plus 1K. So equal to 1 milliamps. So that means I1 is 1 milliamps. So I1 is entering. So plus 1 milliamps equal to 0. So therefore my AN is equal to 3 milliamps. Right? So I got my IN. Okay. What about my RN? Well, my RN is, right, I have to turn all the sources off. So I have 1K, 2K. Current source, open it up, right? Voltage source shorted like this, AB. So therefore, AB is 2K in series with 1K equal to 3K ohm. So my RN is 3K ohm. So my Norton equivalent circuit consists of IN 3 milliamps, RN 3 kilo ohms, right? Did I remove anything out at the beginning? This let's call this RL, right? So therefore, RL reinserted. So this is your final Norton equivalent circuit. Okay, right. Okay, so therefore, this is Norton equivalence, Norton theorem. Thank you.